Okay, so in this problem, we've got an asteroid heading directly towards the Earth. So here's the Earth, here's our asteroid heading directly towards it. It's got an initial velocity of 12 kilometers per second, and that's when it's at a distance. So this distance here is 10 times the radius of the Earth. So that's not drawn to scale. And we're asked when it gets to the Earth's radius, so when it's at 1 Earth radius, what's the final velocity equal to? So in order to do that, we're going to need to assume that energy is conserved, which is reasonable since it says that we can neglect the effects of the Earth's atmosphere. So the Earth's atmosphere would provide air resistance, which would be a non-conservative force, which would lead to energy not being conserved. But because we're allowed to neglect that, we can assume that it is conserved. So assume energy is conserved. Then we have the initial potential energy plus the initial kinetic energy is equal to the final potential energy plus the final kinetic energy. And so we can write down our expression for potential energy that we've just learned. We've just seen that this is equal to minus g. Now this is the mass of the asteroid. So this has got mass little m, and we'll let the Earth have mass me. So it's minus gm times the mass of the Earth over the radius. And this initially is at a radius of 10 times the radius of the Earth, plus the kinetic energy, which is a half times the mass of the asteroid times the initial velocity squared. And this is equal to the final potential energy, which is minus g times m times the mass of the Earth over, it ends up at the radius of the Earth, so 1 re, so that's here, plus a half mvf squared. Now every term has a mass of the asteroid, so we can cancel those out. What we're trying to find is this final velocity here. So let's write a half times v final squared is equal to, we'll move this one over to this side, and what I'm going to do is times the top and the bottom by 10 so that it's got a common denominator with this term. So this is equal to 10 g times the mass of the Earth over 10 times the radius of the Earth, and then we've still got this term minus g times the mass of the Earth over 10 times the radius of the Earth plus a half v initial squared. So 10 over 10 re minus 1 over 10 re is equal to 9 over 10 times the radius of the Earth times g times the mass of the Earth plus a half times the initial velocity squared. Okay, so now we've got an equation. Now we can substitute in our numbers because all these things are known off our data sheet, and this thing was given in the question. So we've got 9 over 10 times g, which is 6.673 times 10 to the minus 11, times the mass of our Earth, which is 5.972 times 10 to the 24, all over the radius of the Earth, which is 6.371 times 10 to the 6, plus a half times. Now the initial velocity was 12 kilometers per second, so that's equal to 12 times 10 to the 3 meters per second. So this is 12 times 10 to the 3 squared. So on the calculator, we put this in. This first term here is 5.630 times 10 to the 7. This second term here, the kinetic energy term, is 7.2 times 10 to the 7. And solving that, we get 1.283 times 10 to the 8. So that's a half times the final velocity squared. So we need to double it and then take the square root. And when we do that on the calculator, we end up with 16,019 meters per second, which we can write as 16 kilometers per second to two significant figures.